If you have heard terms like OSI model, TCP/IP model, IP addresses, subnets, routers, switches, modems, etc., and it doesn't make any sense to you, then by the end of this video, it will make sense to you. I promised it. But before we get into that, I want to mention a few things to you. And those things are like, first, we are going to understand things from the first principles. Yeah, like going all in. I won't be like throwing jargons at you and expecting you to know those things. And the second thing is to have some patience. Yeah. So have some patience, like by the end of this video, I'll interconnect different things. Like at one point you might think, why is he even teaching this thing? Because that's a prerequisite for understanding other things. So we'll connect all of them together and then everything will make sense. And another thing is know what you know. Should I write this? Okay, I'll just dictate it. Know what you know and what you don't. Though knowing what you don't know is a major problem in itself. Like, I'll mention to you, if I'll throw some jargon at you, then I won't tell you that you should know this. Either I'll explain it from the first principles, or if it's an abstraction thing, like these things are kind of topics from other domains, then I'll let you know that this is an abstraction and I'll guide you in the right direction what you should look for. So now we are going to talk about how computers communicate with each other, aka computer networking. But before we start, we are going to always ask this question, why? Why do we even care about this thing? I mean, what's the purpose? So, humans have always wanted to communicate at a very high speed, and that should be reliable and efficient. So, suppose there's a human being here, and there's another human being here, and they are probably like thousands of kilometers away. Let's say 10,000 kilometers. And this guy needs to convey an information that's really important to this guy here. So, how could he do that? Well, he can hire some other guy whose job is to deliver messages. So, what he would do is give this man a small piece of information he can carry and then just deliver it here. I mean, this sounds crazy. You can travel the whole world just to deliver this information here. But there are several problems here. One thing that could happen is like he's gonna travel 10,000 kilometers. So there could be a war going on here between two civilizations, and this guy could get killed. So this guy won't get this piece of information and won't even know that someone was going to deliver this message to him. Another thing could be someone could threaten this guy to tamper with this piece of information. So yeah, I mean, this is not reliable, this is not efficient. We need to figure out a better way. And then their telegraph lines were introduced. So an electrical line was laid down between 2 points, and then you can just use Morse code to deliver some information. Now I want to guide you to a book you should read, and the book is called The Hidden Language of Computer Hardware and Software. And you'll get to understand how telegraph lines were introduced, how this form of communication came into existence, and finally into the computers. Right? So, this is important, but this is not a prerequisite. So, I'm just giving you a brief overview of the history of communication, not in very detail though. But you know that humans always wanted to communicate at a very high speed and in a reliable way. So then computers were built at some point in time of history. We built some computers, and then the problem was that we have some files stored here and some other files stored here, and we want them to share. Well, one thing could be you can get a pen drive, a floppy disk, a hard drive, store some information from here to that drive, and then use it here to get that information. But mind that this computer should support the reading and writing of data on that kind of disk. So there should be some kind of hardware in that and some kind of software that can do this process. So yeah, we just wanted to do this, but then another thing could be who would deliver this hard disk at a very large distance. I don't know. I can't. So then we can communicate these two with a wire, like telegraph lines were done. And we are going to talk about that how we can connect two computers together with a cable, some kind of cable. Let's call it an Ethernet cable. Yeah, we are going to explain what it is, like how we do it, and then how we can change the voltage level to communicate between them. But yeah, before we do that, let's understand some prerequisite for these things. How can we store any kind of information using numbers? Suppose I have some text here. Now, how can I convey it to you? Well, I can say hey. Or another thing could be like you are standing at a very far distance and I do something this 2, 4, 1. Now, these are just some numbers I deliver to you using some sign, but how could you make sense of this? Well, I can do one thing. I can say A stands for 1, B stands for 2, C stands for 3, and Z stands for 26. So when I say 3, 2, 1, I won't speak, I would just show signs to you. Then you would make sense that yeah, this guy means C, D, A. So any form of text, for example, a and a dot. Well, I can give a dot to 27. Any form of text can be represented using numbers. I can just write down some numbers here 7, 21, 22, 6, and this would mean some information, right? Well, text can be represented using any form of information, and why are we like even caring about representing them in the format of numbers? Because computer works on binary data and that is a number system. Well, now I can represent any text as a set of numbers and then I can convey that information to you. But what about an image? Suppose I have an image, then how can I represent this as a set of numbers? Well, for that you have to understand a few things. Yeah. So whatever the object you have, then when I say the color is blue, it's not the property of this object. Okay, do I have to change this? No. So it's not the property of this object. It's some perceptual experience created in your brain when the lights come and hit your eyes. Okay. So for example, light have different wavelength, and for that jargon you have to understand what a light is, what an electromagnetic radiation is, probably go to the rabbit hole of atoms and try to understand these things. But that's not the scope of this video. If you want to understand about this thing, then just go and study about this, because we are not gonna pretend that we know these things, at least for now. So yeah, because I could like give you the usual definition of a wave, of an electromagnetic radiation, of a color or everything, but I won't do any justice to my philosophy of understanding things, and I don't want to do that. So feel free to just go and search on the Google or have some chat with chat gpt and try to understand things from the first principles. I'll come back to it sometime later, but for now understand that when light hits your eyes there is some perceptual experience created in your brain. And another thing is there are like a light has a wavelength, right? You understand this. So there are like some sensors in your eyes, uh, S and L cones, I think that's what they call this. I don't remember the exact names, and who care about the names, I'm sorry for the crackers. But these are sensors for wavelengths of light, and these detect the intensities of light closer to the wavelength of red, green, and blue colors. So that's why any color that can be perceived by these kind of cone cells in your eyes can be stimulated, note the word stimulated, by three colors. RGB, red, green, blue. You take three LEDs, red, green, and blue, and fire some light from them at different intensities. So when the light is fired from these LEDs at different intensities, then it's gonna hit your eyes, and these sensors are gonna detect these lights because their task is to detect the intensities of these three different colors because of their wavelength. So if there were like another kind of cell here, cone cell here, then we would use another kind of color to stimulate that color. But why do we even care about this thing? Because we can have now like three LEDs here, what is an image? It's a grid of pixels, right? Not grid, it's a grid of pixels. So there is like grid, and for each pixel there are like three LEDs here. Think of it red, green, and blue. Like now I can fire these different pixels at different intensities, and now these are gonna hit my eyes, and some perceptual experience is gonna be created. And that was the reason that we had RGB here and not RGY or some other color, because these three cone cells uh, detect or sense these kind of wavelength that matches to red, green, and blue. So I hope that makes sense. So for example, now I can represent this whole image as a set of numbers. How? For the first pixel, I can say 71, 21, 211. So what this represent is like I'm telling you the intensity of red, green, and blue colors out of 255. Okay, if I say 255, 255, 255, it is saying that red, green, and blue LED lights are firing the light at their highest intensity. So why out of 255 and not 100? Because your computer uses 8 bits to store these numbers, and it could be any higher number if your computer uses more bits to store these colors, and those would be more accurate, I guess. Yeah. So now and then you can like represent second pixel as another set of numbers 21, 22, 23, and so on. And you can just take every pixel out of it and represent them using numbers, and you're done. You can represent now any image using a set of numbers. And then you have a video. Video is nothing but images playing at a very high speed, like a set of images, and now they are just playing at a very high speed. So image is nothing but these grids of pixels plus timestamp, like at what time which frame needs to be appearing on the screen. So you can like now store any kind of information using just numbers. Now we were using decimal number, but we can also use binary numbers, right? For example, hi, how can I say it in binary? Well, I'm not gonna say hi, but I can say A, B. So for A, I can say 0. For B, I can say 1. For C, I can say what? 0, 1, 0, 1, 0, sorry, 1, 1, D for D. Yeah. So these are the first four numbers, and then I can go ahead and write more binary numbers again: 0, 1, 0, 0, 1, 1, 0, 0, 0, 0, 0, 0, 1, 1. So these are the next numbers, and if you are curious about why I follow this format like 0, 1, 0, 1, 0, 1, 0, 0, 1, 1, 0, 0, and so on, then you gotta understand about how number system works. This is the foundation of this thing, and for that I would recommend you another book, and the book is called Understanding Numbers for Elementary School or something. I don't remember the exact name, but I'm gonna write it down here or check the description part. And it's by the author Hung Si Woo. It's a very good book, and it talks about like the really fundamentals of mathematics. Have a look at it. So now any kind of information can be represented using numbers. This is what we have till now. Now you have to understand this another concept, that the set of bits, suppose for example 10101, can be represented using any physical property that exists in two distinct states. For example, I can have a set of boxes here, and I can fill in some water in some of them. For example, here is water and here is water. So I can say, because this box exists in like two states, either there is water inside it or there is no water. So I can say if there is water, I can say 1, otherwise 0, 1, 0. So any physical property that can exist in two states can be represented as binary data. Then since your computers uses transistors and electricity, so what we can do is we can define this thing like this. If we have a voltage of plus 5 volt or greater than that, then we can say it's a 1, or if it's less than, then we can say 0. So for example, we can take a wire uh, and then measure the potential difference of it with respect to the ground, now using a voltmeter. Now this is some another jargon of electricity, and you need to understand what voltage is, but for now consider it a form of abstraction, that it's a property of some material which you can measure using some device. So if that device shows like 6.2, then we can say it's a 1. If that device shows like 0.2, then it's a 0. Like greater than 5 volt, greater than or equal to, it's a 1. Less than or equal to, sorry, less than 5 volt, then it's a 0. So I think you understand this now, that we can use voltage levels to represent binary data, right? For example, uh, in your RAM we use capacitors, and if capacitor holds some charge, then it's a 1, and if capacitor doesn't hold any charge, it's a 0. So there is like a grid of capacitors in your memory. This is one capacitor, this is another capacitor, this is another capacitor, this is another. So if there is a charge here, suppose here is a charge, and here is a charge, and here is a charge. So what binary information does this convey? It conveys 0, 1, 0, 1, 0, 1. This is the binary data stored in your random access memory. We use capacitors there in some kind of random access memory. Then for hard disk, I think, like where you store information and you turn off the power and still you have information persisted there. So we use magnetic direction, like for example, your magnetic field might be in the north direction, so I can say it as 1, but if it's in the south direction, I can say it as 0. So it's just a physical property that can exist in two different states, and one of that state we can call 1 and another state we can call 0. Like it's just a way of using those numbers as physical attributes of something. So now we know that any bit can be stored as voltage levels. Now I'm sitting in my room with two computers and some information on one of them, and I need to share that information on this device. So what's the solution? I talked about one of those could be like using some form of floppy disk or anything, and just getting it here and sharing. But another one could be I can connect them using a wire. It could be a copper cable or something. Then you know the voltage level thing. If it's a plus 5 volt, I can say it's a 1. If it's a 0 volt, I can say 0. Make sense? Yeah. So what I'm gonna do is every second, suppose first take the binary data you need to transmit. Suppose I wanna transmit this. Okay, yeah. So first one, and just convert it to the voltage levels first. It's like plus 5 volt, 0, 0, plus 5 volt. It's also volt. Okay, I'm just not writing this. Okay, I wrote it. Then 0, 5, 5, 5. So this is the information we need to convey. So what we are going to do is on every second, we are going to change the voltage of this wire. We can say we can set plus 5 volt for the first second, then as the second ends we can set its voltage to plus 0 volt, then for the next second also it's going to remain the same, for the next second it's going to be plus 5 volt, then again it's going to be 0 volt, 5 volt, 5 volt, 5 volt, and this computer is going to read, it's going to have some hardware that can make sense of the voltage here, like it can read the voltage level here. This computer is going to have that hardware, and this computer is also going to have that hardware that can like set the voltage level of this wire. Okay, so this computer is going to read, no, this computer is going to read the voltage level on this wire every second. 1 second pass, okay, it's a 5 volt, then it will convert those data using some hardware. Okay, it's a 1, and store it somewhere in the memory. We have hardware for these things. Okay, so yeah, then for the next second it's gonna look and it's gonna see 0 volt, 0 volt. So this is crazy, right? We used a wire, we connected it between these two computers and just change the voltage levels, and now we have transmitted our data. So this is the start of our communication between two computers. Nice, this is crazy. Now suppose we have many computers. C1, I'm just gonna use as a point for a computer now. C2, C3, C4, and C5. These are the 5 computers I have. So what are the ways I can share information between them? Well, one of the way could be I can connect this computer to this one, then I can connect this to this, this to this, this to this, then again this to this, this to this, this to this. Like every computer is gonna be connected to every other computer. This is already connected to both of these, then this and this. About this, yeah. Yeah, so every computer is connected to every other computer. If this needs to share information with this, it's gonna go over this copper cable. If it's gonna share information with this, it's gonna go over this copper cable. Like we are gonna flip the voltage level every second over here, and this computer is gonna read information from there. But suppose there are like 100 computers, so I have this computer. So this computer needs to be connected to 99 other computers. So one port is going to use this. Another port is going to be connected to another computer. We are going to use another port to connect to another computer. You think your computer is going to have like 99 ports? What if there are like 1000 computers? It's going to have 999 ports, input output ports. I haven't seen any. So this is not the right way. Like between two computers, it's okay, we can do it. But between 100 computers, 1000 computers, this is not the right way. We need to figure out a better way. And that's where the switch comes in. What is a switch? Well, forget the term. We are not gonna talk about the jargon here. We are gonna understand things from the first principles and why we need to understand it. So the problem is that we have to connect every computer to other computers, right? Every computer is connected to another computer. Every computer is connected to every other computer. Yeah, sorry. We need to solve this problem. What if we have a single device to which every other computer connects? Okay, every other computer is connected to this single device, and this device is gonna take those voltage levels and decide where to send it. Oh, nice. So this means that a computer is not gonna be connected to 3 other computers, but we are gonna break this link. It's gonna be just connected to a device here, and this computer is also be gonna connected to this device, this also, this also, this. If this computer needs to communicate with this computer, it's gonna ask this device, and let's call this device a switch. That's the name we gave it. So this computer is gonna ask this switch, oh hey, deliver this data to computer A. Yeah, this makes sense. But how are we gonna do this? Because while sending information, what we sent is like, okay, plus 5 volt, plus 0 volt, plus 0 volt. How is the switch gonna make sense of this information? How is the switch gonna know that I need to send this information to A or to B or to C? How is it gonna do this? Well, another one of the simple approach could be this switch can, like plus 5 plus 0, this switch can set the voltage level of every wire over here to the same voltage, so every computer is gonna receive the same information. It's also gonna receive 1 0 0 1 0 1 1 1. It's also receive the same data, it's also gonna receive the same data. So every time you send it to A, it will also be received on B and C. Every time you send it to B, it will also be received on A and C. You don't want this. There is something called security, privacy. So we need to solve this, and let's solve this. Now to solve this problem, you have to think from the first principles, and the principle could be like, suppose I sent some data here and I just want it to be sent to C. How can I do this? Well, you have to think that there should be a way to identify the computers uniquely. That's only the way you can send them uniquely. Like if you just want it to be sent to C, then you also have to be able to identify it uniquely. So for that, you know that you should know this, that every computer has a some kind of electronic circuit or something, a card, electronic card. This is called NIC card. Every computer is gonna have it. This kind of hardware is embedded into every kind of computer, even your laptop. And this NIC card has a MAC address, like some kind of unique address, like your home address. You have a unique home address. So there is some number. You can think of it as a number that's hard coded in this NIC card of every computer, and every computer is gonna have a unique MAC address or a unique number associated with it. Think of MAC address is a unique number associated with every computer. It's gonna be hard coded into the hardware. So yeah. So what we can do now is we were sending voltage levels across this to transmit binary data. And suppose I was sending high. High will be converted to binary data using some form of encoding. Have a look at UTF-8 ASCII encoding. That's similar to the way we talked about mapping A to 1, B to 2, some kind of similar kind of thing. Okay, so have a look at it. And high could be converted into some binary data. Okay, but this is not enough. If I send this binary data like high to switch, it's gonna be like, okay, where should I send this? But what I can do is, this is our data. Okay, think of it as our data. What I can do is I can wrap this data with some other metadata. I can be like, okay, here goes the source MAC address, and here goes the destination MAC address, or I can just add it here at the front, destination MAC address. So suppose the MAC address of this is 2, the MAC address of this is 1, the MAC address of this is 4, and this is 3. Now this is not so simple. MAC addresses are not so simple. They have a fixed length. Have a look at it. But what I can do is, instead of sending this data 100101, I can add the destination and source MAC here. What's the destination MAC? Destination MAC is, suppose I'm sending from A to C, so it's gonna be 2, and source MAC is gonna be 4. Convert it to binary. It's gonna be 10, and it's gonna be 100012. Yeah. So when this binary data, it's gonna be 1 1 0 0. Well, let's like this. The number of bits used here is different than this, and if the MAC address is a bigger one, then the bits are gonna be different. So let's just append zeros here to make it a fixed length, 4 bits maybe. Yeah. So the data is gonna be 0010010010001001. Now this A is gonna change the voltage level every second on this wire. It's gonna be like 0 volt, 0 volt, 5 volt, 0 volt, 0 volt, 5 volt, 0 volt, 0 volt, 5 volt, and so on. Now this switch is gonna receive this data. Yeah. Now this switch is gonna extract the first 4 bits, the next 4 bits, and the rest of the data. Now we know that the first 4 bits is a destination MAC address. How we know this? Because we set the rules. We are the ones who set the rules, and we are the ones who designed this hardware component. So we are gonna write some logic in some hardware component of the switch that's gonna take the first 4 bits of this message it receives, and based on this it's gonna check the MAC address of each device, and it will know that the MAC address of C is 0010, so it's gonna just forward it here. Yeah, that's it. We are gonna send some metadata to switch so that it can forward it to the right point. But how is it gonna know the MAC address of C, B, D? So the first time it receives this message, it's gonna be like, okay, I need to send 0010. I don't know who the damn who this guy is, 0010 MAC address, who this guy is. It's not gonna know. So it's gonna forward this message asking for who is 0010. Maybe it will send the data along with it, and then it's gonna receive it. B is gonna say, no, I don't have this MAC address. C is gonna say, oh yeah, I have this MAC address. So it's gonna send the data back again to it with this thing 01000010, because destination MAC address was this for this. But because this C is sending the data, so the source is gonna be 0010, right? Source and destination MAC address are gonna flip. Now switch will see that, okay, this port of mine, let's say these ports have a number A, B, C, D. It's gonna notice that, okay, port C has 0010. So what it's gonna do is it's gonna create a table for itself, and it's gonna store this information. So next time this message comes, maybe this time I send different data. So it's gonna know, okay, 0010, it's gonna check this table here. And oh, C, port C, I'm gonna send some data on this port. And yeah, it's done. So this is how it's called, I think, MAC address table for a switch. Yeah, kind of. So now we can send information between different devices at a very quick speed in a very reliable way. And for now, we just had destination, source MAC, and data. But in practicality, like when you see in the practical world, there are gonna be other headers. And because this thing is very complex, we are understanding it at a very foundation level. So these are enough, but this is gonna be a very complex thing. There is also gonna be some other metadata included here. So which is gonna extract that to get some information about the data it received. So yeah, and we give it a name frame. That's just a name you should care about. We just call it a frame, nothing much. You might notice that we are always understanding things from the why perspective. Like why we introduced the switch here? Because we had to connect cables between every computer so that they can communicate. We did not want that. So we solved that problem. But there might be another problem. Have a look at it. Now let's talk about another scenario. Suppose you are sitting somewhere here with a computer A connected to computers B and C. Here is some other network, some other set of people sitting maybe somewhere in USA. Yeah, these might be in Japan, and again India, and these again might be in India. So now what we can do if A wants to communicate to F, like what's the procedure we need to follow? Well, one of the simple approach we can follow is connect every switch to each other. Yeah, this will work. I have connected all the switches together. So now what's going to happen is, suppose A wants to send some data to F, and the MAC address of F is 0110 and MAC address of A is 0001. Is it fine? Yeah. And again, have a look at the format of MAC address. The format of MAC address is defined and the length, so it's easy to extract it and maintain some consistency. Yeah. So now we are gonna send some data. It's gonna be this 4 and 48. This data I need to send from A to F. Now what we are gonna do is we are gonna first wrap it around with some destination and source MAC address, because switch needs to know where to forward the data. So we'll take this data and wrap it with source and destination MAC. What's the destination MAC? 0110, and source MAC is 0001. Now these set of bits I need to send to S1. So S1 is gonna get this. I'll change the voltage level every second. Well, that's not practical though. Like every second, if you are changing this voltage, then how many seconds it's gonna take? 16 seconds. 16 seconds just to transmit this data. Well, that's not how it happens. It's very quick, like milliseconds, nanoseconds, I guess. I did not look it up, so I just came up with milliseconds or nanoseconds, but it's very, very quick. Just remember that. But for ease of understanding, we are just believing that we are just gonna look at every second. So every second, switch one is gonna look at this wire and see, okay, I've got 0 volt, I've got 5 volt next second, I've got again 5 volt for the next second. So it's gonna take these details and find out that the destination MAC address is 0110. Well, it will see that neither B or C has this destination MAC address. So, like, what happens when S1 gets a MAC address? It doesn't know. It forwards the message to all of its ports, like except the one that sent it. Switch one knows that A sent me the data. How switch one knows this? Well, that's how we designed it. It can know. It has a hardware chip inside it, written with some software, so it can know. We created it as an engineer. So it's gonna get some data and it's gonna see its MAC table. It's gonna have a MAC address table with address here and port here. So it's gonna see that okay, 0110 is not known to me, like where it exists. So it's gonna forward data here. Okay, B is gonna say, oh no, this doesn't belong to me. C is gonna say, oh no, this doesn't belong to me. Then it also needs to forward to this port. Now data is gonna go to S2. S2 will receive the destination port 0110 and it's gonna see its MAC address table, if you can see. And again, it might not know where 0110 reside. So it's gonna again forward the data to F, D, and E. E and D are not gonna respond, but F, being the receiver of this, like the original person or original computer who needs to know this, it's gonna reply back. Oh yeah, this is my MAC address. I'm replying with some data. So F can like reply with any data. It depends on F what code you have written to reply. So yeah, and it depends on you. So it's gonna send back and it's gonna store the MAC address and the port number of F, and then it's gonna forward to the source. S1 is gonna receive this message because it came from this port, so it has to forward it to that port, to the source port. So it's going to receive it here and then the S1 will forward it to A. So that's how it happens. What happened if, like what will happen if A needs to communicate to J, then it's going to go here, broadcast here, then broadcast to S3, broadcast here, broadcast here. Now suppose there are like millions of such networks and there might be billions of computers on this complete network. So suppose A wants to communicate to J and there are like millions of computers here. So what's going to happen? Every computer in that million network is going to receive a broadcast that, hey, are you this MAC address? Hey, are you this MAC address? Like every single computer. We don't want that. It's like waste of resources. So we need to find a better way that, okay, I just hope here and I just came to know that, okay, I don't want to check every device, something like that. Like what should be our thought process? Our thought process should be like, I don't want to check every single device. Maybe whenever I just go to this network, I should just know here that if a device is inside it or not. I don't have to go through each of these devices. So then we find out a new way, like this address is not gonna work. And also you sitting here should know the MAC address of J. Do you have access to it? Do you have access to the MAC address of Google server located somewhere in US? No, you don't. So we need a new format of addressing that's kind of hierarchical, and you can use it in a better way to solve this problem. So yeah, people give this problem a thought and came up with a new type of address. So let's say this network, we call it A, network A. This network can be called network B and this network can be called C and other networks D, E, F, G, H. And this device is 1, 2, 3. Like if we want to reference this computer uniquely and anyone can reference this computer uniquely, then we can say A.1 and for that we can say b.4. For this we can say c.8, or even we can have like c.1. Yeah, it's up to us. It's our format of addresses. So yeah, so for example, now a.1 needs to communicate to c.8. This makes sense, right? This is just a new form of addressing we introduced, and you will understand why we are addressing, like why we are naming these computers this way. Let's see. Well, let's connect them together, these switches. So the data is gonna go from S1 to S2, and yeah, there's another issue here now. Switches work on MAC addresses. This is a new format of address. Let's call this IP address. Does this work? You have any issue? I don't, because it's just a new name I gave it, and you can search for the reason why we gave it as Internet Protocol address. It's just a protocol, a set of rules. So what we'll do is we'll just take our data. This is our data we are sending, and here it used to be source MAC address, destination MAC address, but we are going to include two more fields here. Destination MAC address, this is our source MAC address. Then we can add here like destination IP and source IP. Is that okay? Yeah, it's okay. Like we had some bits, then we did some computation on it and added more extra bits to the left of it so that these switches can extract those bits and decide where it should go. But you know, we had already designed our switch hardware and it just extract the first 8 bits because we assume that destination and source MAC address are of 4 bits. So what it's gonna do is it take all the bits together, and it's gonna extract first 4 bits and gonna know that okay, I need to forward it to S2 or wherever it needs to. So we need a new kind of hardware device, and that's called a router. I mean, we can call it a router. Why router? Because it's gonna help in routing. So I'm gonna first connect this switch to a uh, new device, so that it can help us in a way. What way? You are gonna know this soon. Yeah, this is a R2, this is R1, and this is R3. So switch is gonna get this value. Yeah, let's not talk about that first. Let's talk about this new device. So what this new device is gonna do, this is gonna help us in better routing of the networking data. I was just gonna say something, but I just framed my words, you know, as I fumbled. Anyways, so some data is gonna go from C1, and the destination IP is gonna be C.8. So whenever the data reach here, can you easily tell that B, this is a network B, and we are gonna go to C.8. So we don't have to check every device here. Like, of course, B network is gonna have B dot something, and we are going to C dot something. So we don't have to go through each device and check their MAC address. We can just skip this and move ahead. Then we go to S3, and if there were some other switch with D dot with network D, then we won't even compare it to that. We will just skip it and move ahead. And then we come to C. Now, yeah, our destination is C.8 and our network is C, so it's definitely gonna be inside this C.7, C.8, and finally we reached here. So this is kind of logic we need to implement in our router hardware. So here is what's gonna happen. Look, switch works on our MAC address and it needs to. So this is what we are gonna send using some voltage levels connecting by wires or maybe fiber optics, but we are gonna talk about them later. For now, let's understand this. Now, one more thing you need to know is that when you are on your computer, you know your IP address, right? How does it know its IP address? Because router sends them a message. Yeah, router sends them some bits through which our computers come to know that, oh, this is our IP address. That's nice. So when C1 wants to communicate to C8, that is A.1 wants to communicate to C.8, it knows that C.8 is not in its network. Like if it wants to communicate to A.3, it definitely knows that A.3 is in network, right? Because A network, so yeah, it's gonna be in this network itself. So what it's gonna do is it's gonna write its data, it's gonna write its source IP, it's gonna write destination IP, then it's gonna write source MAC. Source MAC is MAC address of C1 and destination MAC address is of C3. How is it gonna know the destination MAC address of C3? Well, it's gonna like yeah, how is it gonna know the destination MAC address of C3? Well, it can like broadcast the message. Well, there's no way, I think. There's no way that you can know the MAC address of C3 just by sending it some data. You have to know it manually, right? Yeah. You have to know manually the MAC address of C3 and then you are gonna put it here on your own. You have to maybe go to that computer, see its MAC address and put it here. So yeah, it's gonna get this, send it to the switch, and switch is gonna forward it to C3 based on its MAC address table. Yeah. But what if it needs to communicate to C.8? Well, our computer knows that C is not in our network. So what it's gonna do this time? It's gonna put the data, it's gonna put the source IP, destination IP, source MAC. But what about the destination MAC? Well, since it's not in our network, it's gonna put the destination MAC of a router. Yeah, a router has a MAC address, remember that. Because this is gonna handle the part of communicating our data to other parts of the network. So we put the destination MAC of a router. Yeah, not a like C7 or C8 or something. So now the switch is gonna get this, switch is gonna find the port it need to forward the data on, and then it forwards the data here, and router is gonna get this message. Now what's router gonna do? Router is gonna take the data and find the source IP and destination IP, and since it's know that C.8 is not in this network, it has to forward ahead. Now it might be possible that router might have two paths, and router maintains a table called a routing table, and it maintains something like this. For example, it might have that if I want to reach to C, some C network, then I have to go through three hops, and it's on my port number 2. If I have to go to maybe network D, then I have to take two hops. Two hops means one router, second router, first hop, second hop, and it's on my port number 1. So something like this. It maintains a routing table, and how does it know that? Because this router sends a message to this that I can reach to network C without any hop, like just it's directly connected to it. So it will say that okay, I can reach to C network in one hop through port number 1. So it has a table, it knows how to go there. And how it knows? Because routers keep communicating with each other. They keep sending messages to each other. So yeah, they maintain a table. Now what's gonna happen is router receives this and router see okay, I need to go to C, and it already knows that if I just pass the data to this port, then it's one step away from S2. So it's gonna receive the message here, and then it just need to send to C network, and it knows that C is directly connected to me. How it knows? Because S3 is gonna tell S2 that hey, C network is on me. Yeah, like there are some protocols you can look into that helps routers communicate. How do they communicate? Well, they can also send some bytes, some voltage levels across these wires. Who's gonna stop them? We can say like every 30 seconds we can program router such a way that every 30 seconds keep sending such bytes, and those bytes are gonna tell about, like, first 4 bytes might tell the address, next 4 bytes might tell the number of hops it need to take, and so on. I know it's very clumsy, but I hope my words are making some sense. I should have wrote better and drawn better, but that's okay. So the thing is, message goes from C1 to S1, S1 to R1 because we put the destination MAC of R1, and R1 is also gonna mess up with this data because R1 has a MAC address, so it's gonna change the source MAC address now. Yeah, it's gonna change it. It's gonna change the source MAC address from C1 to R1 because R1 is sending the packet, and when R1 will receive it, it's gonna like keep some data about who sent the data so it can forward it back. Just have a look at public and private IP addresses for now, and you will be fine. You'll understand why it needs to change source MAC address and everything. Public and private IP, and why do we need them? Why not just public or private? Now you will notice that we have also solved another problem of ours. We had to manually go to other devices and get their MAC address, but now we can solve this using something called ARP. Like we are gonna do something that's gonna solve this. So what we can do is, because each device now has a unique address, for example A.3 and A.1. So what we can do is, like destination MAC address, we don't really know about the destination MAC address of A3. So our packet will have something like destination MAC address, but what we are gonna write here, we don't know yet. But we know the destination IP address, and we know the destination, sorry, we know the source IP address. So in destination MAC address, we are just gonna write 000. Yeah, because we created our devices such that there is no MAC address 000. Any device won't have 000 as MAC address. So when the switch is gonna receive this, and we are gonna write the logic in switch for that, that whenever you receive a destination MAC address with 0000, just this is, think of it as a broadcast message. So now this is gonna broadcast this message to everyone, and it's gonna ask for, hey, who has this IP address? Because we passed the IP address this time to uniquely identify the device. So C3 is gonna be like, okay, I have A.3, and yeah, I am this device, and here is my MAC address, something like this. Now S1 is gonna get this and forward it to C1, and now C1 can use this MAC address to directly communicate to C3. This is called ARP, as simple as that. Now you can find MAC addresses using IP address. So router solved our problem of infinite check at every device. What happens now is, whenever we create a frame, we pass it to, like not even pass it to, first we check if it's in the same network, then we set the destination MAC of same device in the network, and if it's in no, if I fumbled again, but it's okay. If it's not in the same network, then we set the destination as MAC address of our router because it can handle the rest of the part. Then router is gonna get this message, and it's gonna check its routing table. Should we talk about routing table more? I don't think so, because routing table is nothing but routers communicating with each other, telling about how it can reach other networks. So it can know how it can reach C. It's gonna know that I have to forward data on this port. There might be other port to reach L, L network. So yeah, it's gonna have a routing table, and based on its best guess to reach the network efficiently, it's gonna forward the packet here. Oh, damn, I used the word packet and we haven't even talked about it. We're gonna talk about it soon. It's gonna forward the frame here, and yeah, it's gonna finally reach it here, and it will know that okay, C belongs to me, so I'll just check each of these devices and find out and send it back. That's it. So now using routers, we can communicate very easily. Now suppose that you have to send a 1 GB file, like the size is of 1 GB, earlier we were just sending some 8 bits file, right? But now we have 1 GB file and there are gonna be a billion bits, like a billion of bits. I don't know the exact. So yeah, how is it gonna happen? Then we are gonna have a billion of bits here, 1001, whatever the file is, billions, billion of bits here. Then we are gonna put the source IP here, destination IP, source MAC, destination MAC, and the part in here is called a packet. And actually, let's talk about it later. So yeah, we are gonna put the source IP, destination IP, source MAC, destination MAC, and send it. So let's follow the path of it. It's gonna, let's suppose I want to send from A.1 to C.8. Yeah, this makes sense. So our bits start to go from C1 to S1 to R1. We are gonna put the destination MAC address of R1 because it's not in the same network and it's going to handle the part of it. Now the bits, every bit, like these billions of bits are going to be transmitted to R1. Then R1 is going to transmit to R2 and R2 to R3. Now suppose that while transmitting these billion bits from R2 to R3, you have some error, like some of the bits were flipped. There can be error because this is just a cable, and there are ways using which we can detect that the bits we received on R3 are correct or not. We can't exactly find out which bits were flipped, like maybe 1 became 0, 0 became 1. We can't exactly know which bits were flipped, but we can know that okay, this data is corrupted. So if the data is corrupted on R3 and R2 has sent all of the data, then what's gonna happen? R3 is gonna request this data again, these billion of bits. Okay, send me data again. R2 is gonna ask R1, R1 is gonna ask C1. Let's send those data again. So C1 is gonna retransmit these billion of bits again. This makes no sense. Like then C1 is gonna just use whole transmission line and others would have to wait, but that's not how it works. Like you use frequency to, like you, okay, let's not talk about this for now. But in our current setup, C1 is gonna just use these transmission line for minutes, and if it fails, it's gonna start again, and it has to transmit whole billions of bits. We don't want that. So another thing we can do is, suppose this is our data 1101 and billion of bits. So instead of sending this whole billion of bits wrapped around this, what we can do is select first maybe 1500 bytes, that is 1500 into 8 bits, and then wrap it around here and send it to R1, then to R2, then to R3. Then select the next 1500 of bits, first 1500 bits, sorry, bytes, then next 1500 bytes, the next bytes, and keep sending it this way. But how is C8 gonna know how to join them, like how to make sense of them? So we can introduce a new thing here. Yeah, we can also say send a sequence number here along with that. So when we send the first 1500 bytes, we can also send a sequence number of 1. When we send the next 1500 bytes, we can send a sequence number 2, and then S3 is gonna get all of these bytes together, all of these frames together, and it's gonna join all the binary data together. But suppose while sending the third set of 1500 bytes, some bits were flipped and the data was corrupted. So what C8 is gonna do, it's gonna ask R3, which is gonna ask R2, which is gonna ask R1, and finally C1 for those 1500 set of bytes. That is with the sequence number 3, and it can send just those bytes. So you see, it's easy, and if data is corrupted, you don't have to retransmit all of the bytes. And even when like Suppose C1 transmitted the first 1500 bytes, second 1500 bytes, third 1500 bytes. Then along the way, then once it's done, C2 can start transmitting its bytes. Then again C1 can transmit. So it need not be continuous. This is what packets are. Like you can say this is a packet. Yeah, this whole thing is a frame. This is a packet, but there are like other headers that are put in here for error checking and other things. You can have a look at the official docs, like how an IP packet look like, anatomy of an IP packet. Yeah, you might find other headers as well. Have a look at it. But now we can transmit large files in small chunks, and if there is some error, we can just retransmit that set of data. Now we are happy that we are able to send data from one computer to another computer in another part of the world. But another issue arises. Suppose we send this data 11110011. What does it mean? I mean, is it a text encoded in some format? Is it an image? Is it a video? Like obviously this isn't gonna be a tag, this isn't gonna be a video or something. I guess there are gonna be more bits, but suppose there are like more bits here. So what is it? Is it a text? Is it an image? Or is it a video? That's where application layer protocol comes in. The application you are using can wrap this data in some format. For example, you might see that HTTP protocol is something like this. HTTP, I think it starts with like this: get slash nodes HTTP 1.1, and then you can content type, ask for tell about the content type we are requesting. Well, it's sent by the response. Yeah, I don't remember it, but yeah, if it's a post request, then you can give some headers here and then give some kind of data to the application, like here's gonna be your data. The data can be your name, Shekhar. Yeah, so this was our data, but we wrapped it with this format. So this is what an application layer protocol is, so that when the server or another computer receives this data, it can read it and decide, oh, it's an HTTP request. I can respond according to this. But maybe we were using SMTP protocol. SMTP protocol is used for mail addressing, and if we had to suppose write some mail, hey, how are you? We can't just directly send this text and expect another computer or server to make sense of this. That's why there is some protocol called SMTP, and it describes the format you are going to send your data in. Like you can't just send this text, but I don't remember the exact format, but it could be like send in this format to mail address, from mail address, data here, and maybe host or something like this, or maybe the server it's gonna go to. So something like this, you have to send it in this format. Then on the server side, it's gonna extract these fields and work accordingly. If you send, instead of data, you send here body, and your another computer or server is expecting data, so it's gonna reject it. It's gonna say, oh hey, I don't understand this. We both agreed on some set of rules that we are gonna send data this way, and why aren't you sending this? So I don't make sense of this. So why? So yeah, that's what application layer protocols are for. And have a look at HTTP, FTP, SMTP, and everything. Like for example, there are web browsers. So you don't like create this kind of request yourself, this kind of format yourself. You don't write post slash nodes HTTP slash 1.1 unless you are a low level engineer or something. Web browser does it for you. When you visit google.com, it's gonna write something like get slash http 2.2 whatever it is, and some other headers. So yeah, and this whole data is gonna convert it to binary 10101 whatever it is, using some form of encoding. We talked about it. Come on, we talked about the form of encoding like ASCII and UTF-8. Yeah, we did not talk specifically about them, but we know that any kind of data can be represented in the form of numbers. So it's going to be converted into this binary data. Then it's going to be wrapped around with sequence number, source IP, destination IP, source MAC, destination MAC. It's going to go to switch router, and then through other routers, and finally reach the computer you are aiming at. But let's talk about some OS level stuff. And how this OS level stuff is happening is our concern. Now it's finally the time to wrap everything together, and please don't skip this. Just see this. So suppose you have some data, and using some protocol you are gonna define it. For example, I'm gonna send an HTTP request. So 1.1 slash I want my nodes, get my nodes, and some other headers as required by other computer to make sense of this data, or maybe verify it or something. So this data is gonna be converted using some form of encoding like UTF-8 into binary data by maybe your web browser or something, right? This is some binary you have. Then this binary data needs to be sent to some IP address. That's the primary code. So it's gonna ask your operating system, your web browser engine, V8 engine is running this code. So V8 engine is gonna ask, like written in C, I think, or C++, I don't remember, but that's gonna ask and request the OS to send it to some IP address. What is an operating system, by the way? So you have some softwares, multiple softwares, you have this hardware stuff going on here. Now if you directly give access of the hardware to any of the software, so what it can do, maybe like this is our memory here, this is some data we are storing, 00110101, and so on. Now suppose these first four rows are of software 1. Now, if software 2 can directly access the hardware, the memory, and everything, so software 2 can also access this data, and this belongs to software 1. So, what's stopping S2 from accessing the data of S1 and corrupting it? And it can even like take up every resource of yours, like some malicious program can run and access your memory, and it can just like keep reusing it, and it won't even allow other programs to access your memory. So it doesn't make any sense to give software direct access to the hardware. That's why operating system sits in between, and whatever softwares need, it's gonna ask to the operating system, and it's gonna based on some rules, like maybe if there's just one core, then it's gonna decide which software is gonna run for how many seconds and everything. It can't be like if there's one core then every software is running at once, and it can't also be like software one is running for an hour. We don't want it. We want every software to run properly. So it's gonna ask this, it's gonna ask this, it's gonna ask this that I need to execute this. Then OS using some algorithm is assign them some time slots, and then it can run. The same way, if it wants to access some memory at some address, it's gonna ask operating system that, hey, can I have access at this memory address? Hey, can you give me some 8 bytes of memory? So it's gonna ask the operating system, it's gonna find those memory address and allocate it to. So yeah, it's gonna ask operating system to send this to this IP. Now operating system is kind of software running on your hardware, right? It's also some binary data written, and the program counter is executing it. Have a look at how computer architecture is organized. Is it the right word? I don't know how computer hardware works, and how is computer architecture defined. So operating system is kind of a software, think of it like this, and it has its own separate memory. It doesn't make any sense if softwares and operating system both have the same memory. So this is say kernel memory, kernel aka OS software kind of kernel memory. So what it's gonna do is, okay, I need to send this binary data to some IP address. What it's gonna do is it's gonna take the data, it's gonna add source IP, it's gonna add destination IP, MAC address, destination MAC address. No, not yet. Sorry. It's gonna add source IP and destination IP. That works? Yeah. Now this is gonna store it in its memory. Then what needs to be done is split these things into packets. So OS as a software, it is a software, it's gonna split this data into packets, and then it's gonna add source IP and destination IP. I'm sorry, it's gonna split it like first 1500 bytes, then next 1500 bytes, and then it's gonna add source IP, destination IP. I can be wrong about which of the following is done, but you get the idea, right? And once it's done, it's stored in the kernel memory. Then your computer has something called NIC card I talked about. Then NIC card is gonna, like, it can directly access the kernel memory through something called DAM, direct access memory process. So NIC is a card, it also has some software on it. It takes those packets or whatever the frames they are, whatever you want to call them, these are just the terms. Frames is a better word, I guess. No, packet is a better word, because NIC has access to MAC address as we told. So it's gonna take these packets and add source and destination MAC address over there. Yeah, then it's a frame. So NIC has now these frames and it needs to send it to some other computer. So if it's connected to a switch, then it's gonna set plus 5 volt, 0 volt, or something like that, depending how they are connected to each other. If it's on a Wi-Fi, then they are gonna send some radio waves. And how binary data is represented in radio waves is through something called modulation, like frequency modulation, amplitude modulation, phase modulation. For example, in amplitude modulation, it can be something like this. So high amplitude implies 1, low amplitude implies 0, something like this. Now what a wave is and everything, what an amplitude is, what frequency is. So that's, think of it like an abstraction, and it's part of physics which we are not talking now. And I can like give you the usual definition of a wave, but again it won't make any sense because you can already read it on the internet. I want to give you my perspective of it, and it's gonna take some time. So just think of it as some abstraction that we can send some kind of radio waves that travels in air and use something like this to transmit data. Or if they are on cable, we can play around with voltage and send the data. NIC holds this capability to convert our binary data to maybe electrical signals, to maybe radio waves. NIC has this feature. So yeah, it's gonna reach the switch and then it might reach the router. Now, router might be connected to some other router or something, and instead of fiber cable, we might use fiber optics. That's why sometimes you might hear that a router is connected to a modem, because router doesn't has this capability to convert uh, digital signals to light waves, because you know in fiber optics light pulses are thrown in and that are used to transmit data. If there's a light pulse, it's a 1. If there is not a light pulse, it's a 0. And light can be transmitted at different frequency. So if there are like multiple devices connected to one cable, as you might see, so this device is assigned a different frequency, this device is assigned a different frequency, and this gives a sense of parallelism, because at different frequency we can send data simultaneously and then on the other side it can make sense of it. But I would suggest you to read about waves, frequency, and everything so that you can make sense of it. But now you know that if multiple devices are on the same cable, they can simultaneously send data. A channel is assigned to some devices, and yeah, packets are transmitted through it. So yeah, kernel memory access is required for NIC. It gets this. There's a queue maintained by it because like many applications are gonna send data to it, so it can't send everything simultaneously. It's gonna maintain a queue, gonna forward one, then another one, then another one, and we also forget to talk about port number. Obviously, you should understand this that the data we framed is gonna have more headers, more things here, but now you are capable enough to understand about those protocols. For example, there might be many applications running on your computer. So how is NIC gonna deliver those data to a specific application? Well, there is a logical mapping, something called ports. It's like a logical number, nothing much. It's just a number, and it's gonna be stored somewhere in the memory that this application is assigned this number. A port is just a number, think of it like this. Then whenever a port 2 is received, then we are going to send the data to this application. Whenever port 3000 is received, we are going to send data to the mapped application. There might be a name of the application like Brave browser is mapped to 3000 port. So whenever the packet holds the port number, yeah, we are going to add here port number also. Source address, source IP address, destination IP address, sequence number. Then we can also add port number about the application it needs the data to be sent to. So that's pretty much it. You can have a look at it. You can have a look at how waves work, what modulation is, and how operating system works, how computer architecture is defined. I mean, there's a lot to know, and I told you about what you know, what you don't know thing. So have a look at it, and I suggested you some books, so have a look at them as well. And my next goal might be not like just after finishing this video because I'm pretty bored about this topic now, and I'll look out for something else, something that interests me. But I'll soon, not soon, I won't say, but sometime, someday, soon enough in months, I'm gonna do this thing practically. Like maybe I'll buy Raspberry Pi or use my two computers and buy some electrical components to demonstrate this thing on hands. Like, yeah, it would be fun to create our own protocols. So, yeah, we are gonna do this someday, but now you know me, I don't stick to a lane. I try to do different things which interest me, and if I force myself to stay here and do more things, then I'm getting bored and it won't be like really good.